Hey guys, welcome to our lesson for section 3.2, Properties of Logarithms. This section is going to build up a few different properties. We're going to do a few different really useful tools, and what this is going to really build into is solving exponential equations using logarithms. It's kind of one of the big key takeaways. So when I say an exponential equation, what I'm talking about is something where we have, like, say, 5 to the x equals 82. Okay, being able to solve a problem like that. Something where, first of all, it's not a perfect power. It's not something like 5 to the x equals 125, which you've seen that example a few times, and we know x is 3. But what happens if I do something like 5 to the x equals 82, where it's not 25, so x isn't 2, it's not 125, so it's not 3, it's somewhere in between there. How do we figure out what that number is? And that is where logarithms come really useful. So first I want to really kind of define this really nice relationship. We kind of saw it in 3.1, and we're going to talk about it really and exclusively nail it out. So very simply, if a is greater than 0, b is greater than 0, and b does not equal 1, then the following equations are equivalent. Okay, and what does that mean for these two equations to be equivalent? It just simply means that we can jump from one form to the other. It's something similar to like 2 plus 5 equals 7, and 7 minus 5 equals 2. Those are kind of equivalent equations kind of thing. And so what we get is we get that log base b of a equals c. This is equivalent, and so I'm going to put kind of like this thing here, just kind of representing that we can go from one form to the other, the equivalent equations. It's the same as b to the c equals a. And so this relationship here is really important for you to be very comfortable with, and comfortable not just kind of that it exists, but being able to fluidly move between the forms. So this right here, we call this the logarithmic form, and this we call the exponential form. Okay? This relationship is crucial to being able to utilize and understand logarithms and their relationships with exponentials and to solve equations. What's really nice about this is, notice it's really simple in that the base of our logarithm becomes the base of our exponential, and the other pieces just flip spots. They flip sides of the equal sign. So if you're going from the exponential form to the logarithmic form, your bases are the same. Here, the c is on the side with the base, so over here the c is on the side without the base. It's kind of a nice mental way to remember this, what's going on. When you get into the next math class, Math 111, we'll talk about inverse functions, and this relationship becomes even more clear and more obvious. So let's use this. Let's practice doing this. We're just going to first practice just switching from form to form, and then we're going to practice using this idea to help solve equations. So first, I'm going to write a few different equations down. I want you to convert it from either the log form to the exponential or the exponential to the log. That's it. Other way around. So here's 4 expressions. I just want to convert these from whatever form they're in currently. These first 2 are currently in log form. These are in exponential form. And I want to convert them to the other. So that means I'm just going to write these little arrows. This is our way of writing that we're converting it. Really simply, we just use the fact that the bases are the same, okay, in all of these examples. So let's focus on this first one. The base is still 2. So since we're in log form currently, We want to convert this into exponential. So the base of the exponential is 2. And since the 3 is on the side without the base, it becomes to the side with the base. So it now is here, and that equals 8. And lo and behold, that's a true statement, right? 2 cubed does equal 8. Same thing here, our base is 5. That becomes our base of our exponential. The 0 is on the side without the base, so that comes over here. And anything to the 0 power is 1, right? That was one of our exponent rules, really nice and useful. Now here, this is an exponential expression. We want to convert this to a logarithm expression. So I'm going to first write my log, so I know I need that. Now what base of the log do I use? Well, I use the same base as the base of this exponential. The base of this exponential is 4, so we use log base 4. Now, since the 64 is on the side that doesn't have the base, it goes to the side with the base. Means the 3 must go to the other. And it's that easy. Same thing here. We have log base is 2 of 32 equals 5. So that's it. That's how easy it is to convert these log forms to exponential forms to log forms. We just have to really kind of keep that base the same and just flip the other pieces. That's it. So now how can I use this to solve equations? Well, what if I have something like, say, the log of log base 3 of x equals 5. Solve x. Well, up until now, like, if you would have looked at this and been like, how in the world? Well, this isn't really something we have a lot of confidence with or knowledge of logarithms, right? But exponentials we might be a little more comfortable with. We definitely are a little more comfortable using our calculators and solving things with. So let's convert this from log form into its exponential form. And in doing that, the base stays the same, so I have base 3. Now the 5 is on the side without the base, so that comes over here. That equals x. Oh, look, x equals 3 to the 5th. So we just grab our lovely calculators, right? Unless you know 3 to the 5th by heart, which is good if you do. And that is a lovely little 243. So this tells me that my solution here is that x is equal to 243. Now it's always a good idea just to double check and make sure in your mind, okay, does this break any log rules, right? Because we have those restrictions for logs and exponents. Namely, the bases have to be positive and not 1. And for a logarithm, the piece inside here has to be greater than 0. Greater than 0, so we're good. All right, that's nice and easy. What if I have something more complicated? What if I have something like, let me get a good example so I don't give you guys something crazy. Let's solve this. This is about as crazy as we're going to get, with the exception of what's inside here could get a little crazy too. We'll do an example like that in just a second. So think about any problem you've ever solved before, right? We always, what's our goal when we're solving an equation? Isolate our unknown. Our unknown is x, so we need to isolate this, which means I need to undo this addition, and then after that I undo my division. So first thing I would do is add 24 to both sides. We have 42. Now I just need to divide by 7. So I get that the log of x is equal to 6. Cool. Now this looks exactly like this. Now you may be going like, wait, that doesn't look exactly, there's no base. Oh, but remember, there's a special logarithm that we write without a base. What is that logarithm? That's right. The common log. The common log is log base 10. And whenever we want to write the common log, we just write it without a base. So that means what we're referring to here is actually the common log. We're using base 10. So this equation has an equivalent exponential form of 10 to the 6 equals x. So that means x is equal to 1 million, or 1 followed by 6 zeros. That's not too bad, right? We can just follow those simple steps. Now let's do something a little weirder, okay? Yeah. Log base 3, 2x minus 5 plus 7 equals 11. Okay. All right. I still have something going on outside my logarithms. I still have to get rid of that first, just like we did on this problem. So here, since I'm adding that 7, I need to subtract that 7 from both sides. And I get log base 3 of 2x minus 5. 11 minus 7 is a lovely 4. Now, I can't do anything with the 2x minus 5 because that's trapped inside that logarithm. So I have to get rid of that logarithm first. And the way we do that is we simply convert from log form to exponential form. Base here is 3. Other side is 4. We get this. Well, I can simplify 3x 3 to the 4th. That's 81. Now that's an easy equation. We've seen equations like this, right? This is just a lovely linear equation. 81 equals 2x minus 5. So we add 5 to both sides. 2x equals 86. Divide by 2. X equals 43. Double check my work. So, this is how we deal with logarithmic equations with unknowns. It's really a simple idea. We want to isolate down so that we have just the logarithm of something equals a number, if we can, and then we go from there. Now, let's do another problem. Because all of these have the unknown inside the argument of the logarithm. But what if I have something like make sure I mental math right. Yep. So, how do I solve this? This time the unknown is the base. But that's okay, right? We don't really have any idea how to do that here, but let's convert it to exponential form because we know we can do that. And sometimes just convert it to exponential form, it looks different, but we go, oh, I know how to solve that one. So let's do that. So the base is always the same. The base here is x, so the base becomes x. 6 is on the side without the base, so we get this. Ooh, we know how to do these, right? These are in that form of that b to the n equals k, right? Where we had to ask ourselves, is n even or odd? If n was even, we had to ask if k was positive or negative. Ooh, that's nice, right? We can deal with this. So in this case, n is even, so we have to worry, is this positive or negative? It's positive, so there is a solution. Matter of fact, the solution is plus or minus the 6th root of 64. That's awesome. So this means the solution is x equals plus or minus the 6th root of 64. Do that in our calculator, and we get plus or minus 2. Can there be 2 solutions? No, right? Because what are the restrictions on the base of a logarithm? Well, this equation here has 2 solutions. Because where that x comes from is being the base of this original logarithm, it cannot be both of those things. In fact, it has to be the positive version. So what we can do is something like cross this out, or what I like to just do is kind of rewrite again in a simple, single, clean version. The reason why x can't be negative is because our restriction for logarithms were that b had to be greater than 0 and not equal to 1. Negative 2 is not greater than 0. So that cannot be one of our solutions to this equation, even though in that solution process it came up as a possible solution. So we have to be careful. That's something called an extraneous solution. It's not something we're going to delve into a whole lot now, but it's something that you can kind of be aware of. Extraneous solutions are simply possible solutions that come about in the solution process that are not actually a true solution to the equation. So we have to be careful for things like that. For the most part, I'm not going to give you too many things, but just remember, bases have to be positive. So if you get a negative answer, either it's not that one, it's the positive one, or it is no solution. All right, you guys. That's pretty easy, right? All right, we got this. Now, let's talk about something else. Okay. So we're going to talk about something called the power rule of logarithms. Normally when I give you guys a rule, I like to kind of explain it and kind of talk about how it comes about. But for the purposes of this lesson, we're not going to do that. If you are curious about where this comes about, email me or Google formulation of the power rule or derivation of the power rule. And there's really kind of some not too crazy ideas. It's pretty easy to understand. But what this really comes from, it comes from the relationship of logarithms and exponentials. And some of those rules kind of overlap and kind of have some similar kind of log rules and exponent rules. And if you remember, if we have a base raised to a power raised to another power, we can multiply those exponents. And it's kind of a similar idea here. And what that log rule states is very simply log base b of a to the p. So a is raised to some power. Okay? This is equal to p times log base b of a. So if I have the logarithm of something raised to a power, I can bring that exponent out front and multiply the logarithm. And that's a really useful idea and a really useful trick that we can use to solve these kinds of problems. Or not these kinds of problems, but to solve problems using this. And so what we get is some very nice things. So what if I have this? And let's just, for right now, we're not going to solve it. We're just going to simplify this. We're going to rewrite this using the rule of logarithms. Okay? Well, that just says I can take this exponent and bring it out front. So to rewrite this, that just means it's x times log of 3. That's it. It's really that easy to use, really that useful. Okay? Now, to make this super useful, this tool right now is pretty powerful, but to make it this incredible tool we're going to use a lot of, we want to explain this really cool property of logarithms, and really it's a property of functions. Okay? So if you remember, we have logarithmic functions, right? What does it mean for something to be a function? I'm reaching back, really back and far now, but what does it mean for something to be a function? Think about it for a second. Look in your notes, pause the video. Okay, a function is a relation that has, for every input, there's exactly one output, right? So if I put one thing in, it's only going to give me one thing out, okay? If I put two things in that are actually the same, and I put that in, it's still only going to give me the one thing. So if I say, 0.5 and 1/2, they're equivalent. If I put both of those things into the function, one at a time, I'm just going to get the same thing out both times because they're really equal things. And so what's cool about that is we can say if A equals C, okay, and A and C are greater than 0. Okay. So if we know that these two things are equal, then log base B of A is equal to log base B of C. So if I have an equation, I can take the log of both sides. That's what this rule says. That's what this property does. And what's really awesome about that is that's super helpful. Is because what if we have an equation like, I don't know, say 3 to the x equals 81. Now we know this, right? We know what this is. What is x? I'm sorry, it's 4. right? And I could convert this into log form, and I'd get x equals log base 3 of 81. We evaluate that, and we get 4. But let's do it. What if we didn't know what this was? What if we had no idea? What if this wasn't a whole integer value? We can use this to help us. Now notice, it doesn't say what the base has to be. It just says the bases have to be the same. What would it be a good base to choose so that it would benefit us the most? Well, what base do we have on our calculator? We have base 10 on our calculator, so I can use base 10 here. So let me do that. So let me take the log of both sides using log base 10, or the common log. And so by this rule, these two things are equal. So that means that the log of 3 to the x must equal the log of 81. All right, that's using this rule. Cool. Now, is there anything else that we can do here? Well, I have the log of something to a power. I can use that power rule we just talked about. So I can take this x and I can move it out front. And when I do that, I get x times the log of 3 equals the log of 81. Okay, cool. I have an x, but I have these weird... But what are these weird things? These weird things are just numbers. If there's no more variables left within the logarithmic expression, it's just a number. Just like pi or e or square root of 2, right? It's some number. We may not know what it is exactly, but it is some number. And so we can treat it as if it's any other number. We could treat this as if it was x times 4 equals 17. All I do is divide by this log base. Log of 3 on both sides. Now these are the same things, so they cancel out. And I'm going to draw something up here. We get x equals. Now, a really common mistake is to say, oh, I have log, cancel that out, 81 divided by 3. That is absolutely incorrect. Do not cancel logs like that. The log is not a thing to be canceled. The log is a function, so it has to be incorporated as this whole thing is one thing. This is not one thing. This whole thing is the piece. We were able to cancel them here because the whole thing, log of 3 and log of 3, they were both the same. Since they were both the same all the way, we were able to cancel them. But here we have log base 10 and we have log base 10, but the arguments are different, therefore they're different numbers. We cannot cancel them out. And so what I end up with is x equals log of 81 divided by log of 3. Now I want to grab my calculator and I want you to do the same because there's some really kind of crucial important things to have here. There's some really common calculator mistakes that can give you really weird answers. So what we want to do first is we want to use our log button. We want to say log of 81. And we need to close that. That is the most important thing right here. Have to close it. And then we divide by the log of 3 and we close that again. We hit enter. We get 4. We knew that's what it was. We get that this is x equals 4. We knew that going into the problem, which was easy, right? That's why this is a nice problem to work with. But let's look at what log of 81 is on its own and what log of 3 is on its own. The log of 81 is 1.908485019, and that goes on forever. And log of 3 is 0.47712125547, and that goes on forever. There's no way looking at that I would go like, oh yeah, that's going to be... Clearly, if I divide one by the other, that's 4. Exactly 4. But it is, and that's the cool thing about logarithms. Now, I want to show you one of the most common mistakes I see with logarithms on calculators, and that is not closing that first parenthesis. In particular, log of 81, and then divide log of 3. And even if you close that last one, we get something really weird. What your calculator read, and I'm going to type this, I have a kind of a nice calculator so I can do this. So what your calculator sees when it does that is this. This is what your calculator just did. Because you didn't close that parenthesis on the first 81, after that first 81, it put the log of 3, that divide by log of 3, inside that first logarithm argument. That's how we get that answer. So this is what you have here. So this is kind of what that would look like. So it's crucially important that when you're typing this in your calculator, you have to include that end parenthesis, otherwise you'll get wrong answers every time. All right, so that's a really cool thing we can do with these. Let's do some more problems. Look at some more useful tools. So let's solve 2 times 3 to the x to 94. Okay. Now, what do we do? Well, one of the things that I see that happens all the time and that is so wrong, don't do this. So right now, put your pencils down. Don't write this down because I don't want you to even have it in your notes and mistake it as a fact. I see a lot of students will take this and go like, cool, multiply 2 and 3 and I get 6 to the x. That is so wrong. Just remember, PEMDAS, parentheses, then exponents, then multiplication. We cannot multiply the 2 and the 3 until we deal with that x. Since we can't deal with that x, we cannot multiply them. And since we're solving for this, we need to follow our rules, right? To solve for that, we need to isolate the piece with the x in it. So in this problem, that's the 3 to the x. So I need to get rid of this 2. Since it's multiplying that 3 to the x, the opposite of that is division, so I simply divide both sides by 2. I wrote this wrong down. Sorry about that. Thought that was going to be interesting. Nope. $52. Sorry. Okay. 52. So our initial problem is 2 times 3 to the x equals 52. Looking at different problems, combining things. So, still the same thing happens, that just changes what are equals. So 52 divided by 2 is 26. Well, 3 to the x equals 26. 3 to the third power is 27. So that doesn't work. But that doesn't mean can't get an answer. That just means it's not a whole number. That's okay. Because what I can do now is I can use logarithms and take the log of both sides. And again, we're going to do the one that we can do in our calculator. So we're going to take the common log of 3 to the x equals the common log of 26. And now from here, it's pretty much the exact same as it was on that last example we just did. The only difference is it's 26 instead of 81. So I'm going to use the power rule to bring this exponent out front, giving me x times the log of 3 equals the log of 26. Divide by the log of 3. Giving me x equals the log 26. Now, before we even solve this, what two numbers is this between? Is this between 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5, and so forth? You may be going like, how in the world am I supposed to know that? Well, it comes from looking at this and remembering powers of 3. I mean, powers of 3, right? We have 3, 9, 27, 81, and so forth. So 3 to the second power, 3 squared is 9. That's not big enough. 3 cubed is 27. That's too big. So that means this x value should be somewhere between 2 and 3, closer to 3. Right? So that's just kind of using some ideas of what we have number-wise to make an educated guess and to be able to kind of check our answer without really doing any rigorous checking. So now let's grab our calculator and we're going to do the log of 26 divided by the log of 3, making sure we close out that parenthesis on that first one. Hit enter. 2.966. It's always good to go 3 decimal places unless you're told otherwise. Now this is not equal because we had to cut things off, so we say this is approximately 2.966. And then we have it. And we could check that by going back to our very original problem, and we could just do that in our calculator. Now remember, since we got an approximate solution, we should get approximately 52. So we're just going to say 2 times 3 raised to the 2.966. Okay, so that's putting in our approximate solution into the original problem. Now we should get approximately 52. 52.02. That's pretty dang close. And so that's how we can deal with these problems. And now any more complexities in these, if this x was, say, 2x plus 5, well then once we got down to here, we would have 2x plus 5 equals this, which then we would subtract 5 and divide by 2. And we just use our calculator to handle that. And that's it. That's how these problems go. They're really kind of nice, simple, easy things that we can just follow our basic steps. The new stuff is taking the log and using the power rule. All right. Let's move on to something called the change of base formula. It's something we've kind of already seen a little bit of here. So what if I have an expression like, say, log base 5 of 81, and I want to know what this equals, so I'm going to say it equals x. Now, if you remember, we have talked about this, right? 5 squared is 25, 5 cubed is 125, so this x is going to be somewhere between 2 and 5, or 2 and 3. How do I figure this out? I don't have a log base 5 button on my calculator, but what I can do is I can change this from its log form to its exponential form. And let's do that. And so I end up with 5 to the x equals 81. Now, this doesn't really make it any better, any more obvious of what x is going to be, but I know I can solve this equation because we've just done this like a few different times, right? We had 3 to the x equals 81, 2 times 3 to the x equals 52, right? So what I'm going to do is I'm going to take the log of both sides, and I'm going to be smart about it. I'm going to take the log I have in my calculator. So I'm going to take common log of 5 to the x, plus common log of 81. Now, as you get more and more comfortable with this, if you want to jump straight from here down to what I'm going to have in this next step, that's okay. If you want to jump saying, I'm taking the log of both sides and applying the power rule, if you're comfortable with that mental jump, I'm perfectly okay with that as well. So we end up with x times the log of 5 equals the log of 81. Now I just simply have to divide by log of 5. That goes away. So this tells me that x is equal to the log of 81 divided by the log of 5. All right, I can figure this out, right? We can do this in our calculator now. But x was also this. So if x is equal to this and x is equal to this, that means that the log base 5 of 81 is in fact equal to log of 81 divided by the log of 5. That's really cool. And what I can actually do is I can build a general rule that can allow us to change the base. So notice we had base 5. Now these are base 10. I can change the base of a logarithm using this formula. So the change of base rule so we say for positive real numbers A, B, and C, where B does not equal 1 and C does not equal 1. So we have these kind of conditions on here just to make this all fit together. We can say that the log base B of A is equal to log base C of A divided by log base C of B. So what we can do, what this says, is I can take any logarithm with any base and any argument, as long as it's a valid one, right? So B is greater than 0, not equal to 1, A is greater than 0. And I can change the base to whatever I want. The C could be any number that's positive and not 1. So any number that satisfies the conditions to be a base of a logarithm. And I can change this base to be whatever I want. Now, in our situation, we're typically going to choose C to be 10. And the reason for that is because it's in our calculator. And that's it. Just as we did here, right? So notice I have log base 5 of 81. we change it to log base 10 of 81 divided by log base 10 of 5. Now the way I remember this very kind of simply is the base of my original logarithm goes into the base or bottom of the fraction, and that's kind of my way of not flipping these over. Okay, so let's go back to this problem. We have 5 to the x equals 81. Let's solve this. We've now converted from our base 5 into base 10, and we can now get an approximate value using our lovely calculators. And so we just do the log of 81, close that parenthesis, divided by the log of 5, making sure we close everything, and we get 2.730. 2.730. I know I showed the calculator up there pretty quick, but you guys can pause the video. So that's it. That is our tools that these logarithms give us. These are super powerful tools. Now, one thing you're going to be able to do with these now is some of those problems, those word problems we had from the last chapter, chapter 2, we talked about exponential functions. We'd get to things and we'd have some like expression of, say, the half-life or something like that. We'd say things like, okay, this expression, this bank account balance can be represented by, like, say, 5,000 times 1.04 to the t. And we asked questions like, how much is it worth after 20 years? How much is it worth after 50 years? Now we can ask questions like, after how long will this bank account double? So let's look at that. So the made-up problem I had said that the amount in the bank account after t years was 5,000 1.04 to the t. So let's talk about where this equation would come from, what situation this would be involving. Right? If we remember back to our exponential functions, this is our initial value, and this is our growth factor, right? And this in particular is growing, and so our growth rate here is 0.04. Because remember, our growth rate is b minus 1. So 1.04 minus 1 is just 0.04. And so this would come from a situation where you invest $5,000 at 4% annual interest. And that's it. So let's talk about this. How can we say, okay, when will this double? When will it triple? Okay? Well, let's look at it. So when will it double? Let's just start with that. After how many years will it take for this to double? Well, it's like, okay, well, what do I set this equal to? Well, we set it equal to double our initial amount. If our initial amount was 5,000, that means our doubled amount would be 10,000. This is an exponential equation. We've talked about how to solve these. We just did that a few times, right? I divide by 5,000. I need to isolate this piece here. So I divide by 5,000. 0, 4, 15. 10,000 divided by 5,000, that's 2. Oh, that's interesting. We were talking about a doubling, and it just was this part equal to. And from here, now we just use what? Oh, logs, right? I can use the log. I can take the log of both sides. So I get the log 2 equals the log of 1.04 to the t, which then I can use the power rule. So I can take the log of both sides, and then since I have the log of something raised to a power, I can use the power rule to bring that power up front, and we're almost here. We divide by the log of 1.04. And we get that t is approximately log of 2 divided by log of 1.04. 17.673. So what that means, what that tells us, is that if we invest $5,000 into a bank account at 4% interest annually, it will take approximately 17.673 years until our money doubles if we do nothing. All right. What if I invest $10,000? What if I invest $100,000? How long will it take for it to double? Not for it to gain 5,000, but for that initial amount, we have to double. Well, what's really cool is it actually doesn't matter what amount we have, because our equation so this is our amount in the account after t years is the principal amount, the amount we initially invest, times 1 plus our interest rate as a decimal, raised to the t. So in this case here is 1.04 because we had 4% interest. 4% is 0.04 is a decimal. 1 plus 0.04, 1.04. For this to double, we're going to look at, okay, that means this needs to equal 2p. My first step is divide by p. So I get 2 equals 1 plus r by t. Just like what we had here. So if I say I invest money into an account that gains 6.3% interest. So 6.3%. And I want to know how long until this bank account triples. Okay? Do I need to know how much I invest? No. Because ultimately what I'm going to get is I'm going to get 3p equals p divided by p. And so what I end up with is simply 3 equals, since my interest rate is 6.3, that is 0.063. So I get 1.063. This would tell me how long it takes for the amount in my account to triple. Because for it to triple means I multiply the initial amount, p, by 3. Well, I'm multiplying it by this number. So when will this number be 3? Use our logarithms. We've done this a few times, so I'm going to jump some steps. I take the log of both sides, move by t, divide by that, and what I end up with is t is actually, when I'm going to write this, t is exactly equal to the log of 3 divided by the log of 0.063. Which means t is approximately 17.982. Now you may be going, wait, our last answer was 17.6, so it didn't even take another full year for it to triple. But remember, that was at 4%, this is at 6.3%, so that made things go a little faster. All right, there we have it. How do you feel about logarithms now? Now, there's one more cool thing I want to do with our calculators. I'm going to do that in a separate video for you guys, so that way it's easier for you to follow. Unfortunately, my calculator screen share app thing is not working at the moment, so I'm going to try and find a video online for you about how to do that. Hopefully in future terms, if this is in the summer of 2020, I'll have my own video up for this next section, but if not, that's why. All right, you guys, I'll see you next time for section 3.3.